Our next talk is by Professor Weizhang Ye, National Tsinghua University Chair Professor. His work focuses on AI robotics and reliability, leveraging NVIDIA eye-sensing and Omniverse. Today, he will present a novel approach to improving real-world robot navigation and its integration with our NVIDIA ecosystem. Please join me in welcome Professor Ye.
Good morning. I'm Weizhang Ye from National Tsinghua University, working with Qichen Fu at NVIDIA. Some of our results are already published in peer-reviewed venues. The others are on the journal review. Today, I will show you how to make AMR navigation not only fast, but deployable. Generalized navigation, the data corridor framework, utilize delta corridor spatial modeling to achieve smooth generalized navigation with eye-sensing and GPU. By applying continuous safety corridor, it supports mobile, robust, both and autonomous vehicle in dynamic environment. Delta corridor enables smooth, stable navigation under uncertainty. This slide shows a fast and slow architecture for AMR navigation inside the delta corridor. On the left, system 1 is fast and reactive. And AMR agent tuned by SSO runs within the pre-compute delta corridor boundaries. It handles real-time obstacles avoidance with low latency actions, typically under 15 microseconds per state. So the robot stays smooth without needing global replanning every moment. On the right, system 2 is slow and deliberate. DP-BET estimate the corridor level success and tracks how uncertainty grows along corridor segments. When the corridor qualified drops below a threshold, system triggers corridor regenerate and updates execution boundary for system 1. And the button in the loop, generate corridor execute with system 1, monitor with system 2, and deploy only when uncertainty grows. Fast reinforcement learning executes inside the corridor, delta corridor, while DP-BAT monitors corridor quality and trigger replanning only when needed. Here is a common operation failure, stop and go oscillation. The robot keeps replanning, stops, and oscillates, while obstacles and uncertainty appear. This hurts throughput, increase wear, and can actually raise safety risk. The key reason is that smoothness and shortest path doesn't tell you the probability of success under uncertainty. Next page, please. This is the first key idea. The data corridor, instead of radiating over the entire map, we focus on a narrow band around a reference route. Then we preserve connectivity while proving relevant areas. Next page, please. This slide summarizes why delta corridor is the key abstraction that connects between components. On the left, we use DP-BAT to qualify corridor level success, monitor uncertainty, and trigger replanning only when the corridor quantity drops. This provides a variable criterion for deployment, and it generalizes across domains. On the right, reinforcement learning operates inside the delta corridor, which reduces the effective state space, improves learning stability, and enforce safety by construction through corridor constraints. Reinforced learning then focus on smooth execution and local refinement. Together, data corridor link fast control, while database monitoring enables smooth behavior with controllable updates. Next page, please. Next page, please. We are extending Delta corridor from 2D planning to full 3D safety corridors. In 3D, the corridor becomes a volume around normal route, enabling the SAN operate inside bounds, monitor control quality, and replan only when needed. Principle for area robots, multi-level environments, and slope or elevation award navigation. Next slide, please. Here is the runtime result. We compare against QuickBet, a strong baseline for exact binary state reliability to make the speed up meaningful. Across the grid size, DPBAT is significantly fast with speed up to 157.6 times fast, while preserve exactness. The gap is what makes exact property of success visible inside Nav 2, not as an offline report, but as an online signal to get replanning and prevent stop-and-go oscillation. So reliability can be computed frequently enough to stabilize behavior or not just to analyze logs after values. Next slide, please. This slide shows how DPBAT benefits from GPU acceleration across deployment. Scenarios under immediate addressing for a single AMR on a small grid, the workload is efficient. GPU bound, so GPU bring little gain. However, when the environment scales up to 1,000 times 1,000 grid, the RTX Pro 6000 delivers about 3.5 times. Much bigger, thanks. Which makes real-time corridor evaluation feasible. The biggest jump appears in addressing parallel validation. When we validate many things in parallel, the RTX Pro 6000 reach about 50 times faster, enabling large-scale digital twin verification without slowing down the navigation stack. Next, please. This table shows how Delta corridor compression and GPU hardware accelerate either training. The baseline is CPU only, training without Delta corridor. As the Delta corridor shrinks, the agent trains on a much more effective state space. So even CPU speed improves, we still see a speed up of up to 10 times at a 10% corridor. Adding GPUs amplifies the gain. RTX 5070 is about 2 to 19 times faster, while RTX Pro 6000 scales from about 10 times up to 160 times in the highest corridor. The key message is that Delta corridor gives structural reduction, and GPUs turn that reduction into practical training throughput. Next page, please. This slide shows how System 1 and System 2 loop improve survival as uncertainty increases. Next page, please. If you want a single takeaway, reliability turns navigation from reactive replanning into proactive risk management. That's how we avoid stop-and-go oscillations, and that's how we scale. Next page. Next slide, please. For verification, we use simulation in the loop with immediate addressing and lab. We can make sensor noise, occlusion, dynamic obstacles, and vehicle-based interaction under control scenarios. This lets us tune threshold like tau and validate that reliability predicts Real outcomes before deployment. Sync-to deployment needs measurable reliability thresholds. Next page, please. Let me close with 3 lines. We can compute exact navigation reliability fast enough for online decisions. Data corridor makes the problem controllable. DP bet makes it exact, and Navi2 makes it deployable. Our goal is variable autonomy. Every deploy comes with a measurable probability of success. Part of this work was supported by a media academic grant program, and they leverage a media ISSing. We are exploring CUDA acceleration for heavy parts of DP bet. So reliability can be recomputed at high risk under dynamic things. Before conclusion, I would like to invite my 2 students to present a live demonstration of our system.
Good morning, everyone. I'm Haran Kwan, a student from S2ST.
Will you please click the button? Not this slide. Next one. Yes.
Welcome to Prevent Accidents in Dynamic Environments. We combined a star with our new Manhattan Delta Corridor in IsaacSim. On the right, the blue line is the ASTAR path, and the translucent area is the real-time safe buffer. Traditional ASTAR algorithms are often rigid. They tend to hug walls or trigger frequent emergency stops when encountering pause or hesitate at all, operating at an extremely low computational cost. The system scans the safe area of the forward corridor dozens of times per second. This seamless maneuverability is achieved because our system simultaneously incorporates the Manhattan Delta Corridor and a space-aware bias. Once the system detects that one side is restricted by a dynamic obstacle, a virtual penalty is instantly applied to the ASTAR cost map. Throughout this continuous evasion process, the blue escape corridor consistently and tightly envelops the robot. We achieve this by implementing a unique iterative pruning technique, which systematically eliminates all invalid dead-end branches. The greatest breakthrough of this technology lies in its extreme edge computing efficiency, ensuring robust, real-time navigation without heavy processing overhead.
Hi, my name is Selena Huang. For the next application, Delta character, please help me to play the video. For the next application, Delta character extend from the 2D navigation into 3D spaces. Here is our simulation of wafer and die transfer process. We apply 3D character to simulate the wafer and die transfer to restrict the search space to ensure the reliable, safe, and smooth motion. The first phase is about the wafer handling system. Here, the robotic arm transferred the 300 mm from the fork to the chuck. Because folding wafer is a catastrophe failure, we rely on the character boundary to guarantee collision-free path, allowing the heavy arm to move smoothly without jerky and unpredictable vibration. Next is the die transfer process. Where the arm picks the die from the source chunk, transfer it, and carefully align atop on the logic die. This phase demands that the exact same reliability but executed at much higher speeds. To achieve this, we combine 3D CLODA character with inverse kinematic for rapid planning motion. For this part, we designed the gantry head and the IsaacSim to simulate die pick and place process. Then we utilize the surface scripted API inside the NVIDIA 5.0 to perform the persist arm section. The delta character ensures smooth path optimization, keeping the motion strictly within safe bounds. Finally, we integrate the local LM to automatically input simulation logs and verify results in the bottom right extension box. You can see that there is a red arrow there to see. And looking ahead, we plan to merge this 3D framework directly with a local LLM or reinforcement learning policy in Isaac Lab. And thank you for listening. And next, we will have about 5 more minutes for the Q&A time.
No Q&A. Okay,
No
that's all.
Q&A. Okay.
Okay, due to the limit of time, I'm afraid we have to skip the Q&A session. And that's all the time we have today. And thank you again, Professor Schneider and Professor Ye and the students from National Tsinghua University. Enjoy the rest of GTC. Thank you, guys.
Session. If you are staying in the room for the next session, please remain in your seat and have your badge ready to be scanned by our team.